This phase noise plot shows the phase noise from a source with a 490 MHz carrier frequency. Both random Gaussian noise and spurious jitter, or spurs, are visible. Note, the spurs here are displayed in dBc, that's dB below carrier, not dBc per hertz. The word spur is a shortened term for periodic spurious noise. Because spurs are periodic and typically stationary, they are correlated to something, for example, circuit or PLL artifacts, although it is sometimes difficult to determine the source of the correlation. Spurs are modeled as sine wave modulations of the carrier, and they are considered to be jitter at a single offset frequency. The jitter contribution of a spur modeled as sine wave modulation as opposed to random noise can be calculated and is well known. Typically, only large spurs contribute significantly to the RMS noise. Note that in this plot, the phase noise is being integrated over the offset range of 12 kHz to 20 MHz. The total RMS jitter reported by the test equipment over this offset range is about 339.2 femtoseconds. The RMS jitter number includes both random noise jitter and the jitter due to the spurs. Next, we'll determine the jitter contribution of the two marked spurs, the A spur at -79 dBc and the B spur at -87 dBc, and we'll see how they contribute to the overall RMS jitter of the measurement at 339.2 femtoseconds. Spurs are correlated jitter and can be modeled as sine wave modulation at a particular frequency. The equations shown are used to determine the jitter associated with the spur as shown on a phase noise plot. The required information for this calculation is the clock or carrier frequency and the spur amplitude in dBc. Using the values from previous slide of 490 MHz carrier frequency and levels of -79 dBc for spur A and -87 dBc for spur B, the calculated peak-to-peak and RMS jitter contributions of each spur are shown in the table. Spur A contributes 51.6 femtoseconds RMS jitter and spur B contributes 20.5 femtoseconds of RMS jitter. The contribution of these spurs is very minimal to the overall RMS jitter, as we'll see on this next slide. RMS values add using the root sum square equation. In other words, to calculate a total RMS of separate RMS values, you need to take the square root of the sum of the square of each value. To quantify the jitter contribution of spur A and B, we use the root sum square, or RSS equation, to back out the spur RMS jitter from the total RMS jitter to arrive at the RMS jitter without the spurs. If we solve the RSS equation for the random noise component of total RMS jitter, and then substitute the appropriate values of 339.2 femtoseconds for total RMS jitter, 51.6 femtoseconds for spur A RMS jitter, and 20.5 femtoseconds for spur B RMS jitter, we get a value of RMS jitter without the spurs of 334.6 femtoseconds. Compare this to the total RMS jitter with spurs of 339.2 femtoseconds, and it can be seen that the spurs are a minimal contributor to the total RMS jitter. For many applications like wide area networking, using optical transport networking or Ethernet, RMS jitter is typically the figure of merit used. But some applications can be more sensitive to spurs, applications like ADC conversion and wireless applications. Some phase noise test equipment will allow spurs to be displayed as either dBc, as shown in the leftmost plot, or displayed in dBc per hertz, shown in the rightmost plot. In scaling spurs to dBc per hertz, the single frequency spur tends to get smeared or spread in frequency, reducing their apparent peak levels. Keep this in mind when observing spurs on phase noise plots if interested in actual dBc spur levels. Both representations will give usable RMS jitter values, but with slight variations in value due to the measurement technique used. The DBC or left plot doesn't integrate the spurs, but calculates the spur contribution based on spur level and then adds the contribution into the total reported RMS jitter. This is the conclusion of part 1 in this jitter and PLL tutorial focused on jitter definition, classification, and measurement. Part 2 will focus on jitter characteristics as applied to PLLs and clock buffers.